in the best possible way our original curve in the neighborhood of that point. But it doesn't mean that when we parameterize them, that the parameterizations themselves should be related to each other. You see what I mean? Okay. Any other questions? So, these are tangent lines. And by the way, this includes, for example, the issue of the slope. When we talked about parametric curves at the beginning, when we talked about parametric curves on the plane, we didn't talk about tangent lines. We talked about the slope of the tangent line. But of course, the slope of the tangent line can be easily found in the case of a curve, in the case of a line on the plane, from these equations. Okay. So that's more or less the outline of the material that we learned about curves. There is one more sort of a subtopic here, which is applications of curves. So there are various kind of quantities we learned how to compute related to curves. So there are various integrals, more precisely. Various integrals. So you've got the arc length, right? You've got area under the curve, or an area enclosed by some curves, enclosed area. Let's call it this way. Area, and also surface, revolution surface area. So these are the various integrals which you can set up related to curves. And of course, this is something you need to know, that there's various formulas involved here. Okay, but that takes care of the one-dimensional objects on the plane and in space. And as you see, I kind of organized all this material under one umbrella topic, whereas in fact we studied this material in a slightly different way, so not necessarily exactly the same way. Because we first talked about planes and then three-dimensional space. But I want to emphasize the fact that actually there's not so much of a difference. The way curves are on the plane and in space is actually very similar. Revolution surface. I didn't want to say the word revolution. You know. Big Brother is watching. So I want to be careful. But you know what I mean. Okay. Now, next is surfaces, right? So these are one-dimensional objects. And next we talk about surfaces. Surfaces are two-dimensional objects. And surfaces live in R3. Because you can fit a basketball in a plane, in a two-dimensional space. It has to live in a three-dimensional space, dimension one higher. So what about surfaces? So surfaces, as far as representation of surfaces, they're given by one Cartesian equation. They're given by one Cartesian equation. So remember, for curves, they're given by one parametric form, or we have to do two equations in R3. But now for surfaces, the other way around. We need one equation, but if you want to do a parametric form, we have to choose two parameters. So that means that it's more economical to use Cartesian equations to describe a surface by an equation, as opposed to using parameters. So, but I leave this as a little note. We need two parameters now. And in fact, this is something we will do later on in this course when we talk about various double and triple integrals. We will have to parameterize curves. But for now, we don't really use this method. We exclusively represent surfaces by equations, by a single equation, instead of writing points on the surface in terms of two parameters. And so what comes next is different examples of surfaces, right? And once again, the simplest class consists of linear ones, which are planes. Simplest class. Okay, so what do we need to know to represent a plane? To represent a plane, we need a point and a normal vector. As I remember, we saw in one of the most memorable images from this course so far. You have a normal vector to this plane, and you have a point. And this is sufficient information to describe all the points on the plane. Right? So let me draw it here. So this is a plane, and let's say this is a normal vector. You can see blue. Oh. So now I know when I want to leave a sublime message on the board, I know which chalk to use. All right. So which do you see? The white I hope you see. Although today the board is very white. So let's see. I've got yellow and I got green. Green? Yeah, I think we're all concerned about the environment, right? So let's use green. Is that better? Okay. All right. So we exile the blue. We exile the blue chalk. No more. Only when I want to write something that you don't see. Now, so we have a normal vector. This is a normal vector. And again, we have a point. We need to choose a point. In both cases, lines and planes. Now this n is usually written as ABC, but I don't want to write it as ABC because we already used ABC for lines. I just want to emphasize that this is a different type of vector. Okay, so let me write n d e f. Okay, and so then the equation of the plane is simply d times x minus x0 plus e times y minus y0 plus f times c minus c0 equals 0. Okay. So that's the equation which actually we derived by using dot product in the first place, but I don't want to repeat this now. There's a very simple way to explain why this precisely represents all the points on the plane. So this is an equation on the variables x, y, and z, where all other quantities are given. This is d, e, f are coordinates or components of the normal vector, so they should be given, and likewise x0, y0, and z0 are the coordinates of the point, and they should also be given. You can rewrite this by opening the brackets. Okay, so you can rewrite this by opening the brackets. So what you can do is you can isolate the terms with x, y, and z, so you will get dx plus dy plus fz equals something d, e, f, g. Okay, where g is dx0 plus ey0 plus f z0. right? So this is a number. This is a particular number. So the reason I'm writing this is sometimes you can be asked the following question. Suppose you're given a plane. Let's say you have a plane 4x plus y plus 3z equals 5. Okay. So, and you can be asked, what is the normal vector to this? What is the normal vector? So you just look at the equation and you see right away what the normal vector is. Because these are precisely the coefficients in front of the variables x, y, z. These are the components of that vector. So for instance, you could be asked, here's the equation of a plane. Write down the equation, parametric equations for the line, which is normal to this plane, and which passes through a particular point. So then, what should you be thinking? You should be thinking, what do I need to know to write down the equation of a line? To write down the equation of a line, I need a point, and I need a vector, the direction vector. Okay, so the point, let's say, will be given. So then how do I find out what the direction vector is? Well, the line is supposed to be, in this setting, supposed to be perpendicular. So the direction vector of the line is the normal vector of the plane. And now the point is that you can see it right away when you look at the equation. It's 4, 4, 1, 3 is a normal vector. Right? So the equation contains all the information that you need. And that's how you can you should approach this kind of problems. To write down the equation of the plane, you need to know the normal vector. But conversely, if you already have the equation of the plane, you can immediately find out what the normal vector is by just looking at the coefficients. Yes? What else would you need to do other than find a parallel line? Right. How would you find a line parallel to? Well, so to find a line, just to find a line parallel to a plane is not a well-defined question, right? Because there are many parallel lines to a plane passing through a given point, right? Let's say if you have a point somewhere here and you want to look, there's a parallel plane to this plane, passing through this point. So let's say this piece of paper would be part of that plane. But inside that plane, there are many lines which you can always say are parallel to this plane. So you can't be asked write down the equation of a parallel line. You can be asked write down the equation of a parallel plane. You see, now that is actually a good question. Let's suppose you're asked to write down the equation of a plane which is parallel to this one and which passes through, so parallel plane passing through the point 1, 2, 3. It doesn't matter. I'm just taking random numbers. Okay. What is the equation of that plane? Well, since this plane is parallel to the original one, they share normal vectors, right? The normal vectors are the same. So I might as well use the same normal vectors as for the original plane, which would be 4, 1, and 3, right? So these two planes will have to share the left-hand sides of these equations. We'll have to have the same left-hand side. The only thing that could be different is the right-hand side. And how do I find the right-hand side? Well, for that I use the second piece of information. The second piece of information is that this plane contains this particular point. So for this particular point, the right-hand side should be equal to the expression I get when I substitute the coordinates of that point, right? If I substitute the coordinates of that point, I get 4 times 1 plus 2 plus 3 times 3, right? Which is what? 4 plus 6, 4 plus 2, 6 plus 9, 15. So the equation is just 4x plus y plus 3z is equal to 15, whereas the original one was equal to 5. Right? In fact, so all the planes which have the same left-hand side but different right-hand side will represent planes which are all parallel to each other. But they will pass through different points. Only one of them will pass through a particular point, for example, the point 1, 2, 3. But it's very easy to find the equation of the plane which passes through that point by simply substituting the coordinates of that point in the left-hand side. Yes? So again, there's not a single perpendicular plane to a plane, right? The condition of being perpendicular would uniquely define a line. Right? A line, say, through a given point, through a given point on the plane, there's a unique line which is perpendicular to it. And we just discussed, to find that line, you just need to know the normal vector. But the normal vector you can find out right away, right, from this. Now, there is another question that you can ask, is suppose you intersect two planes and find out the equation of the line, right? So that's a little more tricky. So here you have to take the cross product of the normal vectors. Right? So there are all kinds of, yes? If you're given a line? Okay, so that's very good. So there's a question also, another question that can be asked is relative positions of line and planes, right? So here, so this particular question I'm asked is about relative position of a line and a plane. So let's suppose you're given an equation of a plane, dx plus, let's take this one again. So 4x plus y plus 3z equals 5. And then suppose you have a line. So it's like 1, let's say 1 plus 2t, and then here will be negative 1 minus t, and z is 2 plus t. And so these are typical equations for a line and a plane. And you can be asked, say, do this line and plane intersect, or are they parallel to each other? Because these are really the only options, right? If you have a plane and you have some line, the line either is going to intersect somewhere, this plane, or it's going to be parallel to it, or actually there's one more option where it actually may be part of this plane. And how do you find out? Well, it's very simple. You simply substitute these parametric equations into this formula, and you see whether you can find a solution for t for this equation. If there are no solutions, it means that they never intersect, right? If there is a solution, if there's a unique solution, it means they intersect at one point. And if the equation is satisfied for all values of t, that means it just belongs to it. So in this case, we'll have 4 times 1 plus 2t plus y plus negative 1 minus t plus 3 times 3 plus t equals 5. Right? So we open the brackets, we get 4 plus 8t minus 1 minus t plus 6 plus 3t equals 5. So we get, did I make a mistake? 4 plus 8t, that's right. Yeah, I hope you do it better than I do on Thursday. 4 plus 8t. So okay, now so this for t we get these three terms. So that gives us 10. And 4 minus 1 plus 6 gives us 9, right? Equals 5. So 10t is equal to negative 6. So there is a unique solution, which is 6 minus negative 6 over 10. What did I do? Okay. It's one of those days. So minus negative 4 over 10. But I'm glad that you're paying attention. That's a good sign. Negative 2 over 5. Okay. So what could happen is that it could happen that all the terms with t disappear. It could happen that they all cancel each other out. And then you get a number on the left-hand side and a number on the right-hand side. And then two things could happen. They're either the same, in which case it means that the equation is satisfied for all values of t, which means that the line belongs to the plane. Or it may be, say, something like 5 equals 6, which is wrong, which is false, and therefore the equation is not satisfied for any value of t. That means that they're parallel. Someone wanted to ask me a question. Yes, I answered your question. Okay, good. So, but as you see, the most likely, in a generic case, there will be some non-zero coefficients in front of t, and then there will be unique solutions. So generically, a line and a plane will intersect, but sometimes it could happen that they cancel out. All right. So where were we? I talk about simplest class of surfaces, namely planes, and various questions that could be asked about planes. But these are not the only surfaces we have studied. We have also studied quadratic surfaces, surfaces which are given by quadratic equations. Okay. So the next example is here. T is quadratic surfaces. And for quadratic surfaces, we have an equation like this, except now we allow second powers, squares, x squared, y squared, also mixed products like xy or yz. Okay. So what you need to know here is that we can break that all of those quadratic surfaces break into several major groups. Okay. And how to tell whether a given equation describes a surface in that group, and what are the sort of the quality features of that group. So you've got here ellipsoids, and you've got hyperboloids of two different types, and you've got paraboloids of two different types. Okay. So you have to be able to tell by looking at the equation as to what it represents qualitatively. You don't have to necessarily you will not be asked to draw what is called a hyperbolic paraboloid. Okay. That's not the goal to test your drawing skills. The goal is to see that you understand the difference between different equations that describe quadratic surfaces and what are the salient features of different quadratic surfaces. All right. By the way, when I talk about quadratic surfaces, I did not mention two important groups of quadratic surfaces. So in addition to the ones discussed before, we have these cylinders. We have these two classes. One's called cylinders. And cylinders are surfaces which are described by equations in which one of the variables is not involved. So you could have, for example, x squared plus y squared equals 1. So the variable z is not present in the equation. And it's very easy to represent this. You just draw the corresponding curve on the plane, which corresponds to these two coordinates which are involved. In this particular case, it's a circle. And then you take this, you think of this as a frame, and then you move that frame parallel to the z-axis. And the surface you get by sweeping, which will be swept by this frame, by this curve, will be your surface. So in this case, that's exactly the cylinder. Right. So that's why they're called cylinders, even though the original frame doesn't necessarily have to be a circle. It could be hyperbola, for example, or a parabola. So you'll get sort of a parabolic surfaces. You think of them as kind of cookie cutters. That you just have a certain shape that you want to cut, and then you make a cylinder out of that shape. So that's what those cylinders are. And the second one is second sort of class of surfaces, which we didn't talk about in class, but I want to mention because they're also important, are the cones. Okay, so the simplest example of a cone is given by this equation: z squared equals x squared plus y squared, and that's given by this picture. Well, it's sort of self-explanatory because it is called a cone and it looks like a cone. Except it's sort of a double cone. When you draw it like this, it's a double cone in the sense that z could be both positive and negative, and there is a basic symmetry between the upper half of this cone and the lower half of this cone. If you flip the sign of z, the equation will not change because the square will kill that sign anyway, right? So that's why it has these two parts. So these are the cones. Okay, so planes and quadratic surfaces are the two classes of surfaces we have studied in greater detail than the more general surfaces. And for more general surfaces, we have discussed linear approximation. So again, I would like you to see and appreciate this analogy. For curves, we talk about linear approximation of curves by tangent lines, and for surfaces, we talk about linear approximation of general surfaces by tangent planes. And just like in the case of tangent lines, we have a very efficient method for writing down the equation of the tangent plane. Right? So tangent planes. And so what you need to know here is that if you have a graph of a function in two variables, z equals f of xy, and you have a point x0, y0, and f of x0, y0, which we'll call z0, then you should be able to write down the equation of the tangent plane to the surface at this point. Okay? And the way you do it is it's actually very similar to the equation for the tangent lines. We talked about this last time. So the equation specifically looks like this. Right? So we have two partial derivatives of the function f sub x and f sub y evaluated at this point. This is the equation of this is the tangent plane of the tangent plane to the graph. Okay. You can also be asked to write down the equation of a normal line to the graph. What do I mean by normal line? That's a line which passes through the same point and which is perpendicular to this tangent plane. Right?